Our next presenter is Kristen Eller. Kristen Eller is an environmental scientist specializing in water quality with a particular interest in source tracing. She has worked with solids for almost 9 years, focusing on distribution water quality, source tracing, LCR/LCRI, and emerging contaminants. Please welcome Kristen Eller.
So if you were in our last talk, you have a good idea of the compliance situation that SAWS is currently in for our LCR and LCRR compliance. The Cliff Note version, if you missed that talk, was we have over 350,000 unknowns to uncover by 2037. No, that is not a typo. Yes, it keeps us up at night. We do not have a widespread lead problem in San Antonio. It was never a widely used material. We do have documentation that over 800 service lines were removed in the 80s and the 90s, but we also know there's probably a lot more that were replaced that we just don't have that documentation. So very early on, we knew that emerging technologies might be the only way we could actually achieve compliance. So we started from the very beginning looking at different options. Predictive modeling, which is now an option for all of us, we started looking at very early on, and we are almost about to finalize our predictive model, which we're very excited about. It's going to really help us reach that goal. We've also looked at water quality sampling, conductivity probes, and metal detection technology. And of the three I just listed, that last one, metal detection technology, is far and above a better option for SAWS and for our industry than anything else we have tested. So I would like to introduce you to White River Technologies. They have redeveloped a military-grade metal detection technology for our industry. We have tested 2 different sized units, the Apex, which is the larger unit here, as well as the Mini, which is a much smaller unit that can get into those tight spaces. In between fences, it can go into backyards, it can get around landscaping, and you can still have that successful survey without digging a hole. This is a non-invasive technology that was originally developed for the military to find unexploded ordnances, and it is still used worldwide today. For our industry, this technology is able to differentiate ferrous materials, so that's going to be your iron, your steel, insert galvanized here, as well as your non-ferrous materials, which are going to be copper or lead. It can also tell you plastic by simply not having a signal and being able to turn that water on at that home. There is a subset that is simply cannot analyze. Some yards are going to have too many interferences, and we'll go into that a little bit more, but this is not going to be a 100% successful method, and so you do have to be able to adapt to make sure every yard is going to have a successful survey, even if it's not with this specific technology. So to zoom in on what exactly you're looking at, here's a zoomed in picture of the Apex, and I'll start with these lunar lander tires. They're very bouncy, they're very maneuverable, they're hard to puncture, but they're also very easy to repair. They're great to work with. If you look here, you kind of see these cross beams up here, and there's even a third one down there. Those are the transmitters, which are sending that signal, which is then received by the receivers down here on the bottom. All of that goes up and it talks to these electronics up here. This is going to be the computer, this is the brains, which is then interpreted here on this tablet interface, which provides real-time feedback of what that instrument is doing and seeing at that time. There's also a GPS. Right now they took the GPS off the Apex and they're marking this hydrant location, but normally it sits right up here on this little post, so you have geospatial reference everywhere this goes. As I mentioned, there are 2 different sizes. The Apex, you can see the size is over here. The benefit of this larger unit is you are able to cover more ground faster, as well as have a greater penetration depth. Right now, this one can reach about 3 feet in depth to determine that service line material, and they are currently working on getting it even deeper. The Mini, while you can get into locations that the Apex just simply can't fit into, you do lose a little bit on that depth. It can go to about 1.5 to 2 feet, but again, they're also working on increasing that depth. And especially, at least in San Antonio, that covers nearly all of our service lines on the customer side, if not all. So how exactly does this work? So we've all seen somebody on the beach with a metal detector. Overall, it's the same general principle. However, that one you see on the beach is just looking one-dimensionally into that ground. It says, hey, there's something down there. It may give you a little bit more of information, but overall it says dig and find out. But I think we can probably all agree, for unexploded ordnances, dig and find out is not something you want to do. And so when this technology was originally developed, they needed a lot more information than that, which is why we had those 3 transmitters on 3 different axes. So you are actually creating a 3D analysis field in the ground so you can pinpoint exactly where that unexploded ordnance is, or in our case, we can tell pipe material, diameter, thickness, and sometimes even pipe condition. Whenever you go out to a yard, every test is called a survey. Part of that survey is somebody taking that GPS that we saw them marking on that hydrant and walking around the yard, and you're marking key features in that environment that could cause an interference to the signal. This is your meter box, sidewalks, driveways, hose bib. You are trying to create that physical world into the digital space so whoever's looking at that data can see something in the data, oh no, that's a sidewalk or that's a valve box, and it gives you that explanation and a more thorough evaluation of that data. As the unit passes over that pipe material, it is creating a unique signature that they're able, with the algorithm, determine that material composition. After a survey is fully and complete, it involves a package of analyzed and complete data with match probabilities and a lot of QA/QC checks, which is very important, I think we can all agree, as well as geospatial maps very similar to these. These are actual tests from our initial pilot. And as I'm sure you've been sitting there, you're looking at that, and I bet most of you can find pipes in these maps. These maps are invaluable. For me, I get lost going in a straight line, so if you just show me data without that map, I'm like, I don't know what I'm looking at. This gives you where the house is. You can see, okay, here's the street, here's the house, and so you can see that trajectory and make those assumptions. And is this a service line, or is this just something else in the yard? And these are also rapid results. So often in our industry, we collect a sample and then we wait. And then we wait some more. This is not like that. These are very rapid results. You can get a turnover on these data and this analysis in the same day. You can do it in the same hour if you have the analyst time available. So what does that analyst actually do? They get a completed image, just like this one up here, and they select the pipe. The algorithm and the software that White River has developed is not telling you where that pipe is. It's just showing you what's in the ground. The analyst actually has to select that pipe material. So in this hypothetical case, if I select this black area, this looks like a pipe to me. It's going from the house to the meter box. And then the software will overlay the tracks, the passes that the Mini or the Apex made over that. And it's these intersection points where the black line meets those dotted red lines that are actually analyzed to determine the composition. And each result from a survey will be compared to a library. White River has developed a library of materials by surveying a ton of different materials in a controlled environment to determine what each pipe looks like under these circumstances. Now I'm going to take a second. If you have back home, you have a bunch of lead pipe, I would like some lead pipe. So if you want to get rid of some, let me know. I'll take it so we can survey it more. So once we've done all that and we've evaluated this data, we've looked at those intersection points, we then get this plot right here, and this is a characterization plot. And what this is telling us is what your material is. Now these boxes are still in draft. We are still fine-tuning that a little bit. But I'll start here with the steel box. So when you plot a steel pipe on this range, it's going to be out here in left field, way away from everything else. And this is actually a small box to what it really looks like, which we'll get into an example here in a second. You can see here copper, we have a big pink copper box and a bunch of little copper boxes. Not all copper is the same. There's different sizes, there's different thicknesses, there's a bunch of different conditions, thinner, thicker, everything. So they have actually surveyed everything they could find, and then some, to create all of these different ranges. So each one of these can look a little bit different. This technology can actually tell you the difference between 1-inch K and 3/4-inch K. However, for our purposes, we just need to know it's copper. So that's why we have this outer copper region right here. You may notice this lead is kind of a little wonky here on the bottom, and that's simply because, like I stated at the beginning, SAW has no confirmed lead. We've been trying so hard to find lead. We have not found any. And so we only have almost laboratory results of lead. So we are working with White River, and White River is working very hard to find lead in the field to further validate this lead range. So as we finalize this characterization plot, we will have a more confirmed range for lead. Once we run all the results, this is an example of what your result may look like. It may just show up right here, which is a clear indication that you have just surveyed a copper pipe You can see that separation between it's not steel, it's not lead. You can confirm with that, and you will get a match probability associated with that analysis. So SAWS got started with this. We created a test bed out at SAWS, and we've tested a few different things there. White River was originally brought to our attention by EPA. We had tested a different metal detection technology with them, which wasn't going to pan out. It just didn't have the analytical precision that we really needed at the time. And so EPA introduced us to White River, and we did a proof of concept pilot. That original pilot was 23 locations that we had already potholed. Of that, 12 were correct. Now, that's not a great percentage, but right off the bat, it was extremely promising, and we knew that we needed to see more. So we set up a 6-week pilot where White River came out and they trained 3 staff, the 3 that are actually sitting right up here, to run this for 6 weeks. We had an adaptive approach to this pilot. We weren't going to set our schedule, set our plan, and that was it. We changed things daily, weekly, to make sure that every single time we went out, we were going to be more successful than the last time, to make sure that all the lessons we needed to learn, we could. Part of this pilot, we buried a calibration test bed at SAWS. This is actually it. You can see there's trenches right here. This is before we did close them in. This is before we actually closed in those trenches. There's a copper and a galvanized line still to this day at SAWS headquarters buried in the ground. Every morning, we would calibrate the instrumentation, go over these same areas, and we do so at the end of the day as well to make sure that everything was functioning properly on the unit. We'd also do this with the GPS to make sure that the GPS was functioning properly. So what is really needed to make this work? You need 2 field staff and you need a data analyst back in the office. Of the 2 field staff, there's a survey point lead. That's the person who's marking these points right here across. That's going to be the meter box, the hose bib, the gas meter. Anything that you need to know about in that physical environment for analysis, that person is marking them. They're working through a checklist, which I'll show you a little bit more in a minute, but it helps make sure that all of the right questions are being answered every single time. Meter box inspections are completed. If we're at your property, we're looking in your meter box, we can't stop ourselves. We also take pictures of the area because that provides context for that single day that you were out there doing this survey. There could have been something random in the yard that you didn't see that was picked up, but you can see it in the picture. So those were really worthwhile to take throughout the process. The second field staff is actually going to be your equipment lead. This is the person running the Mini, running the Apex. They're ensuring they're covering the entire area. You actually want to overlap your tracks to make sure you get as many passes over that line. You do it perpendicular to the direction you think the line is actually running in the ground. And that equipment lead is just making sure that coverage that they're doing is as complete as possible. All of this is relayed back to the office almost in real time to the data analyst. They can give feedback to the field staff. Hey, run back to that one that's right down the street. I just need a few more passes. Great, we can do that. They're also completing the final analysis and developing those final reports. Transporting this thing was not simple. You can take the wheels off and you could fit maybe in a really big truck bed, but then you're lifting this up. So we decided to rent just a standard box truck here, and we put a frame in the bottom so we could have really good tie-down points to make sure everything was very secure as we were going. We had this is the front of it here. This is the Mini strapped down in the front where we have different baskets and organization here of keeping charged batteries versus batteries that need to be charging, trying to organize everything as well as we possibly could. You can see the Apex here is tied down, and we had these ramps that we used to get it in and out. It was not overly difficult to get it in and out, but it was definitely worthwhile to line up multiple sites on the street rather than jumping around town trying to get it up and down and up and down. That's exhausting. And so I've been talking about all this, but let's actually see this in action. So this is Dave actually running the Apex, and as you can see, it's not hard. He's not pushing overly hard. It's not difficult to maneuver. You can see every once in a while he's looking down on that tablet. He's making sure he's on track for where he wants to go. Everything in that tablet, you start and you stop a run. Every run, you have to only go forwards. While you physically can go backwards in this, the instrument doesn't know you're going forward or backwards, so the data gets all squirrely. So it's just easier just to always make sure you're recording going forward. And as you saw just there, it's really easy to turn around and maneuver around obstacles. The Mini is very similar. The biggest difference between the Mini and the Apex, besides size, is the computers are actually in a backpack right here that we wore, and White River has been working on moving that down to a different kind of chassis for the Mini, and we're really excited to see that. But as you can see, it's a very similar process, initiating that run on the tablet, and you just simply walk forward, making sure you're on track for where you want to go, not going too fast at the same time. These wheels are not so lunar lander, but they are very easy to move around, and this is a rather light unit. We've been talking about the tablets. I'll give you an idea of exactly what we're looking at. So this is the display field on each one of those tablets, whether you're running the Mini or the Apex, it looks the exact same. You have your address right here. This right here, the CSL, is where we would distinguish between, are we doing the customer side service line or are we doing the utility side service line? You have a speed gauge right here. If you're going too fast, it turns red. Easy to walk too fast with this thing. And you can see right here, here's some example of the actual tracks. So I'm gonna play it here, and you can see right here, we log. Before you do a pass, you hit log, and then when you're ready, you just start walking. And it's actually going to track visually each pass so that it's very easy for that operator to see what area has been missed and to go back to redo it. And you can see that's gonna happen here in a second. Stopping this here, and you can tell it goes green right there as I think this was me walking backwards. You can see going too fast here, it's letting you know, but we weren't logging then, so it was okay. But then going to fill in that gap, and it's very easy just to color between the lines, get everything colored nice and evenly. For the survey points, here's an example of the survey points. So in this case, Dave is just marking this fence. He has a phone. You can also use the tablets as well, just to mark the location of those survey points. He marked the fence, and now he's going back out into the yard to see what else does he need to mark. And the more you do this, the more you get an idea of everything in the yard that is valuable for that analyst to know its location of, to have a successful survey. So I mentioned the checklist. Here's an example of the checklist. It kind of has a few different sections. At the top here is just the general information, your location, how many service lines. In many cases, we'd have 2 service lines right next to each other, and we can kind of get a 2-for-1, where you're going over both of them at the same time and getting a result. You have general information about meter box. So we talked about interferences. So iron meter box cover will be an interference. So we'd pull it off, put it to the side. If we couldn't do that, we'd notate it here. So it's just more of an interference that data analyst has to work through. There's a checklist for pictures, a checklist for GPSs. Meter box inspection information is in here, as well as just general notes, which in some cases was the most powerful thing we did, because you're just notating everything that might be worthwhile to this inspection. And early on, I spoke to adapting to this pilot and making sure we were as successful as possible. We realized that we needed to measure those pipes whenever we could see them in the meter box. However, getting calipers in there is not very easy to do. So we created this highly technical doodad to just measure the circumference of the pipe. It's just a simple string with markings for different circumference levels. As long as we could get a finger underneath that pipe, we could measure that circumference. And in some cases, that was the difference between a successful and an unsuccessful survey, because we could confirm that it wasn't a 1.5-inch pipe. No, it was a 3/4-inch pipe. And that helped that analysis complete. So skip straight over to the results. For this pilot, we did 199 surveys. This does not include the data for the proof of concept pilot. So in total, we did over 200 surveys. Largely, most of our surveys were Apex. We tried to do as many as we could with both units, and that was worthwhile. We were able to get a lot of many sites. But it's interesting how many times we went out, okay, this is going to be an Apex day, and we used the Mini most of the day, because you just never knew what you're going to encounter and what you really needed to do. You can see between the Apex and the Mini, it took about 20 minutes to complete all of those surveys individually. Now, we did learn through this process that we were not doing enough passes whenever we were using the Mini. So I imagine as we would revisit this, that time required for the Mini might go up by maybe 5 minutes or so to account for additional passes that we now understand that we need. We have completed 58 potholes for validation of this test, and overall, the initial analysis shows 70% accuracy, which is pretty good, but it's not great. But in that data that we observed, there's many things that we saw that just needed to be updated, to update that analysis for our industry. One of the biggest was an overlap in copper and lead data, which I think we can all agree we don't want. The smaller copper was overlapping in the data between the larger lead. This is where the diameter came in for us. But also, since that time, White River has redeveloped the algorithm that, for the software to interpret those better. And now we aren't having that overlap like we were before. So that's a huge success for this. We made more definitive plastic determinations, as well as increased QA thresholds both on the data analyst side as well as in the field. Currently, EPA has committed to complete all potholes associated with this project going forward. So as many customers who are part of this original pilot who want a pothole and are willing to let us do that, we will be completing that with the cooperation and the support of EPA, which we're very excited about. So updated accuracy is coming, and we hope to have it here in just a couple of months. So now for some examples. So I'm going to walk through each kind of the pipe examples that we see to give you an idea of what exactly you're going to see. Here's an example. This is going to be a galvanized example on Robin's Rest. The first map you'll see is going to always be your survey points. This house was very early on in the project where we didn't realize the value of those survey points, so we have quite a few less than we do later on in the project. It's a lesson learned right there. But you can see we have a driveway right here. There's a valve box, which I think was mislabeled valve when it really should be the meter box. I can tell you that the hose bib on this house is approximately right here. Behind the hedges is the closest one, so the logical trajectory would be pretty much connecting those two. The first map, or the second map that will look like is a pipe map. So part of the software that White River has developed finds a pipe. So many things in the environment don't look like a pipe. There are depth associated with each one of the analysis. So if there's one here at 6 inches, and then the next one here about, a foot later is at 18 inches, well, that's not a pipe. It's not going to go like that. So this algorithm here takes all of that into consideration of what actually looks like a pipe that can help you interpret where you should be looking. The next map is going to be our ferrous map. So this is looking for anything iron or steel. And as you can see, there's a straight line right there leading from the meter box that glows like a light bulb. I can spoiler alert, this is in fact a galvanized pipe that we have confirmed with this homeowner. If we go look on the non-ferrous map, you may be looking at it and saying, I still see a lot of stuff. Thought it was supposed to be non-ferrous. Well, it is. I want you to think of when you've looked at the sun and then you look away, you still see that sun. The sun is so bright that you have that residual in your eye, and it takes a minute for it to go away. That's exactly what is happening here. Now, I don't recommend you go look at the sun, but I know we've all done it, so I think we understand what we're talking about. The residual right here is basically that sensor is overwhelmed by that iron signature when looking in that non-ferrous environment, that it's going to visibly show that, and you can even see a residual of the pipe itself right there, but if you analyze that pipe, you're not going to get a copper result or a lead result. So here, just like we showed in the example, we've selected this pipe to detect. This is the steel. This is what it's saying, and it's, like I mentioned before, it's way off in left field. You can see that difference between the copper range that we saw earlier and the copper ranges we'll see here in a minute compared to that steel. It is showing a match percent of 100% in this case. These ferrous examples are really kind of the easiest ones because it's really a yes or no answer that you ask right up front. Is it ferrous or is it not ferrous? And then you move on the decision tree. For a copper example, we did this with the apex. Again, start with our survey map. We have a sidewalk and a driveway, meter box. Hose bib is located right here. And this is a logical trajectory, which we started doing not too far into the pilot of saying, okay, I'm out in the field. Where do I think this line is going? Just to give that analyst back in the office a little bit more of information of what might be the service line. As we look at our pipe map, you can see some interferences here in the street from the sidewalk, but you also see a bright line right here connecting the meter box to the house. Go to our ferrous. As you can see, compared to the galvanized example, we have a nice big blue expanse. There is nothing being detected in this ferrous threshold for this home. But if we go to non-ferrous, you can see a very bright line connecting the meter box to the home. We are still seeing that interference, that glare. However, it's not, we know that and we can take that into our interpretation of this data. And so we choose to, before I go show you the results of this one, most of the examples I'm going to show you are from the apex, but the mini works just as well. So here's an example of what the mini looks like. This is a copper determination as well. You can see the sidewalk in here, and you can see a clear line. Here's the meter box going to the house and the hose bib. You can see a clear line there, but you probably will agree it's just a bit messy. And that's what you get with the mini. It's just going to have a little bit more interference, a little bit less resolution, but you still can get a good result. Back to our example from Montfort. If we select this line that we just located, you can see it plots, it's this gray one right here. It is well within this copper region right here, and we have a match probability of 100% at 3/4 inch copper pipe. I did mention that part of the field staff is taking pictures. I'm not going to show you these for every house, but this was a good example of what is being provided to the data analysts so they can see that survey field. You can even see Veronica here going back and forth in there trying to get that survey, just giving context to that data analyst. Here's an example of a plastic pipe, which can always be difficult in these situations. So we have one located on Flint Oak. Here's our survey points. Again, we have some driveway sidewalk over here. Hose bib is right here. Meter box here, and you may see this is not quite a straight line. Well, there's a tree in the middle, and you can't really do a logical trajectory right into a tree. So that's why it's curved a little bit. We go to our pipe map, and we're definitely seeing some things from the rebar in the sidewalk, rebar in the driveway, but there's nothing overly in the middle of the yard connecting that meter box to that house. Okay, interesting. Go to our Ferris, nothing there. Again, we're seeing a little bit of interference, but really not too much, and overall, we're not seeing anything in this map that could connect the meter box to the house. We go to non-Ferris, and we are still seeing the same thing. We still have this interference, and that's just one of the things as you're interpreting these maps, you have to kind of put in your brain. You're going to have interferences, and you just need to ask yourself, is this one that matters, or is this one that doesn't? When it comes to rebar in a sidewalk and determining ferrous material, it's really not going to affect you unless your line is right up against it. So in this case, again, we are still not seeing any line connecting the meter box to the home. This could safely be assumed to be a plastic line. It would fall in that cannot analyze category, but likely plastic material. One of my favorite examples is actually our variable materials. I think we can all agree that from a meter box to a home on every single house that's built in the last 100 years is not going to be one single material. We get frequently questions of, what do you mean you're going to do a pothole? That's right there. How do you know what the rest of my yard is? That's a benefit of this technology, is as part of the survey, you need to walk the whole yard, so you're getting all of that information. So here's an example on Otter Trail. Again, we'll start with survey points here, driveway, sidewalk, meter box, and a valve box here. This green is actually a gas meter. I forgot to put it in the legend. One thing that is important about gas meters is most gas lines are steel. So knowing where that gas line is, knowing where that gas line meter is very important when making a determination. While you may see a steel line, is it the service line? And you always have to stay in that logical field in your mind. Is this a service line or is this not a service line? And follow that decision. If you look here, you can see a clear line right here. So this is the pipe map. So the map is saying that there is something that looks like a pipe running 3/4 of the way through the yard. If we go to the Ferris, nothing remarkable here. We can clearly say if there's anything in there, it's going to be of a non-ferrous material, and something pops up. You might notice that this map is a little bit shifted. I'll talk a little bit more about this here in a minute, but there was a GPS issue that occurred when we were surveying this day, and it was something that we noted between the survey point GPS and the Apex GPS, so we know there is a slight shift in this data because of that. But as you can see here, we have a pipe to analyze right here, but we have a big gap of nothing. We analyze this pipe right here. It comes back right in the middle here. It's clearly a copper. We have 100% match at little over a 3/4 inch copper pipe. But we still have this gap. For us, this determination would be a connection of plastic to copper going into that house. We have potholed this house, and we potholed within about 2 feet of that meter box, and we came up with a plastic pipe as well as the plastic pipe coming out of the meter box, which confirms this in our minds, and it just gives more data for us all to analyze of what is the most appropriate determination when you're making a service line. You're not just depending on one hole that you happen to dig in one location. You are able to view as much of that service line as that survey area will allow. So what have we learned? The process is so paramount with this method. We have been working very diligently with White River to develop a process that is appropriate for our industry, that is answering the questions we need to. But at the end of the day, you have to trust the data that you are collecting in the field so that you can have a process and a product that you believe is as accurate as possible. You have to be adaptable. Every yard is different. Even if they look the same, they're not. It's amazing how many washers have fallen out of a pocket only to be found by this 20 years later, and there's just something bright in the middle of the yard. So you just have to be flexible and to communicate through the issues. Communicate with the other field staff. Communicate with the data analyst of maybe you should go a different direction and you might be able to get a better image. One thing that is important with this is a dedicated charging area, and I know that's kind of a slightly random comment based on the ones I was just making, but there's a lot of things to charge. There's batteries for the Apex, batteries for the mini tablets, GPSs, Wi-Fi's, And so we had to create a very distinct charging area that was as organized as we could possibly make it to make sure everything was charged for the next day. Because if you're not charged when you start that day in the morning, you're not surveying, and you need a lot of redundancy in that to make sure. So it's important when you're planning something like this to make sure you have those little, that seem like little things that can be so vital to the program's success. You need to plan ahead. I mentioned it earlier. This technology is, while it can go from one location to another and you're loading it up every time, you're not going to do it very efficiently. We did as many as 20 in one day with this technology, but it was all on one street where you could walk between them. You also have to be aware of your cell conditions. So I mentioned the Otter Trail, we had cell issues. One thing we realized was in San Antonio, we all know AT&T is the best cell network. Well, White River had T-Mobile, and there was a disconnect between the T-Mobile satellites on that day with our AT&T network, which caused that shift, which is something that we have now realized, hey, we need to ask those questions when you're going to an area so you can have the most appropriate result. You also have to be obviously aware of weather conditions. That's a consideration whenever you're doing field work, obviously. This is a very rugged system. You don't have to worry about getting it rained on. If it does start raining, you can keep going until the rain starts selecting things on the tablet, and then you can't really do much after that. So, it is very rugged, and it is very user-friendly. Overall, the public perception of this has been wonderful. At one point, we were joking that we needed someone along in the field just for crowd control, because people would be coming out of their houses, they'd be stopping on the street, because let's be honest, it looks cool, and people want to know what you're doing. But that was also selling points for us. Of, hey, we can communicate about this project, we can communicate about this program, let's get you signed up. Hey, can I go do your yard? And we got a lot of yeses. But at the same time, those same customers, we heard a lot of, you're not going to dig in my yard, but you can run that thing. Yeah, that's fine. So we think that this type of system is going to be more acceptable both from a cost perspective as well as for our customers of just joining the program because they don't want a hole dug in their yard. Before I get to questions, I just want to do a few acknowledgments. I want to acknowledge the SAWS team, all of us here in the black polos. This has been a huge effort for us, and we've had immense support from SAWS leadership, and we couldn't be more grateful for that opportunity. For White River, they have been a wonderful partner in this. Greg Schultz, who's sitting right over here, is from White River. If you have any really technical questions, I will be pointing you in his general direction. They have been fabulous to work with, and we look forward to continuing this work. I do want to acknowledge EPA and their involvement in this and their continued involvement in this. They've been extremely supportive in helping us take this as far as we have. And while it's not up here, I do want to thank TCEQ and all of their support with this technology from its infancy. Without that, this would not have gotten this far whatsoever. So we do appreciate all of their help and support and encouragement doing this work. And if there are any questions, I would be happy to take them.
I have a couple of online questions, and then I'm happy to run the microphone around. The first question is, can this technology distinguish between the pipe materials and the connector materials which link the distribution and main service lines?
This is not going to be a let's go find a connector type of technology for a few different reasons. Most of your connectors are going to be close to something with iron, like a meter box cover, rebar in a sidewalk. So all of those are just going to have an interference that would overpower that very small connector. If you have a longer connector, quite possibly. But as of right now, that's not really something we're emphasizing as we're developing this further.
Thank you. One more, and then I'm going to run around. Do you share that data with customers if requested? Have you used 811 to help determine lines?
Yes and yes. So if a customer, when we got customers to agree to this program, we told them that we would provide them the data. And unfortunately, that has taken us a lot longer to get there than we anticipated. But we have every intention of when we do get finalized all of the new updated analyses to send a letter to all customers participating, thanking them for their participation and giving them their results. And the second part of that question was, I'm sorry.
The use of 811.
811, yes. We have not. We use that for our potholing efforts. We have not leveraged that for this program. That could definitely be beneficial for any buried electrical lines because an electrical current can affect these results. As far as gas lines, yes, that is something that we have talked about partnering with our gas provider in the city to better say, okay, is the gas line coming from the front or the back? If they can just give me that much information, that's valuable. We even completed some surveys where you could clearly see the gas line going to the gas meter and the service line going to the hose bib, which was really cool to see it working to that extent where you can define that. But at the end of the day, it comes down to that analyst and that team have to decide, is this a service line or is it not?
Do you ever let the other cities around San Antonio use your equipment? Do you come out to the cities and use it for them to let them know?
When we first started this pilot, we reached out to every city within a reasonable driving distance and asked, hey, do you have lead? Trying to find locations that have lead. So we had a lot of really great conversations as a result of that with neighboring cities. And what we really found out is everybody in our area is in the same boat. We don't have lead, but now we have to prove it.
I had a question. In your research and your surveys, did you find any place that may have heavy lead in the soil that may have thrown off any readings you may have had, or different areas of the state that may have heavy lead soils and how that may affect the whole process?
We did not observe that. I don't really think it would be a huge issue unless the contamination was so high that it would just basically show interference across the board. And there's definitely going to be some yards where you have just too much interference and you can't make a conclusive result, and you need to pivot to a different type of inspection. So I would anticipate something like that if the levels are that high. Talking with White River, we asked them, okay, we have iron in our soils. Is that going to be an interference? And what they've said in their worldwide adventures using this technology is really the only places that they have seen that is really in Hawaii with these highly volcanic soils giving a signal. Because you have to remember when you're analyzing, you're doing a large area and you're just selecting what looks like a pipe to find those intersections between those passes. And so with that pipe identification in the algorithm of saying, does it look like pipe? If you have an area that is showing elevated lead or iron in the soils across the board, well, that can be kind of edited out in that software component because overall it's not going to look like a pipe.
Hi, I have two questions. One, can you talk a little bit about how you got customers involved? Like, did you ask for actual access agreements? How did you coordinate that with also trying to optimize, like doing a whole street at one time?
Mm-hmm.
And then second question is, did you do this at all on public side service lines, or was everything just in yards on private side? Could it be used for the public side?
Sure. As far as getting customers involved, we started with existing potholes that we had already completed through our other work. And we looked at streets that were in an appropriately aged time. We tried to get different decades, essentially, as well as, oh, look, here's a cluster of people who are interested in our program. And that's where we leveraged our interest list. We didn't have a signed agreement to go on their property, but they had told us, hey, I'm interested. So we went and we door knocked. And like I had mentioned, that people just literally came out of their houses asking what we were doing. And that was probably the biggest benefit for this whole program, of just the interest in the community of what we were doing. And whenever we explained the program, people were really kind of excited that SAWS was being proactive with this and looking at other methods than what are currently available. As far as the utility side, yes, every survey that we could, which was the most of them, we did do that utility side. Now on the utility side, we are talking about a deeper line, and there's going to be a little bit more interferences. So we have decided to at least focus for just this time on fully developing that customer side, getting that fine-tuned to where we need to, and then reanalyzing all of the data on the utility side. Off the top of my head, I will say that it would mostly be successful on that utility side. You're just going to have way more interferences that you have to deal with, as well as a smaller section that you can do, because likely you're going to be in the street, and the street's only so big, when the yard is usually much bigger.
Are you picking up the lead out of the copper pipes because of the solder? Is that is that what you're looking for on the lead, or is it just a lead pipe?
The goal was to look for lead pipe, and that's really kind of where the hole still exists in this pilot is, since we don't have any lead pipe, we don't have anything to survey, and that's where White River is partnering with some other locations that have known lead in the ground to kind of fill that gap. But I wouldn't anticipate you'd see enough signature from lead solder. It's just not big enough to be picked up on this technology.
I have 3 questions. The first one, what is the rate of the inspections? Like in the test holes, for example, if you're using it, you can get like up to 70 maybe service lines per day. What would be the rate for this technology?
We are estimating, our best day, I want to say, was what, 22? Something like that. And we were flying that day. So, you know, there's definitely, you know, considerations of how long it takes to get places and things of that. But I think realistically, you could plan for 15 to 20 sites in a day. The key of that is going to be lining them up where you can easily go one to the other, and anytime you spend loading up and going somewhere else is going to dramatically affect that. But overall, we saw about a 20-minute survey time. Larger yards are going to be take longer. Smaller yards will take a little bit less time.
Okay, and what about the cost compared to the test holes?
We are still kind of working through that because there's different ways of, you know, do you hire staff to run this? Do you know how to go about all of that? But we're estimating that we're going to be in the ballpark between $200 and $300 per survey.
Okay, and is there any development in like resolving the interference with concrete and roots? And sometimes we need to inspect around roots and concrete.
Yes and no. So the algorithm is able to, if it's a constant interference, it can to some degree edit it out, which is what you kind of saw in those pipe maps, how that interference got a lot better in those pipe maps because a rebar sidewalk doesn't look like a pipe. But it's never going to get, or I wouldn't expect it to get to a point where you can completely edit out that rebar. If you have a lot of rebar, this might not be the best solution because you need to be able to see underneath that rebar, and that iron signature will just overwhelm the sensor to where you can't see below it.
Thank you.
Okay, great. If you have any other questions, feel free to grab any of the SAW staff. Everyone here knows about this program and can talk about it too.